Okay. Hi everyone. Let's get started. Now we will be starting with second derivative test, right? If you recall, then if I just go back to the previous slides, yes, we were seeing the second derivative, and what does this mean? Do you recall what does the second derivative mean? So if I'm saying that f double x is greater than 0, then what does this mean? It means that it is concave up, right? So f double x greater than 0 means it is concave up. And then if I'm saying, see, maybe I can just copy this. So let's just see here. So if I'm saying f double x is greater than 0, then it means it is concave up. Then let's just understand this concave up meaning little more. So what do I mean by saying concave up? So first tell me, this f double x will be a certain point, or like if I just ask you that, okay, what is the value of f double x? Then what will you say? See, this greater than 0 means what? Is this like curve greater than 0 or what? So generally, like we are asking at a certain point, right? So let's suppose I'm saying that f double dash certain point, maybe c, is greater than 0. Then what does this mean? It means at that particular point it will be concave up, right? It will be concave up, which means that at that particular point, see, at that particular point the function will be behaving like concave up. मतलब कि ऐसा हो सकता है कि like for example, let's suppose f double s x or f double s c is greater than 0, then at c I'm saying at c it is concave up, right? So which means what? It means that at c it is concave up and you don't know anything else, which means let's suppose I say that the function is something like this. And if I'm saying that here it is c, and here f double dash c is greater than 0, f double dash c is greater than 0, then do you guarantee that, okay, let's say something like this, okay, do you guarantee that the function will be concave down or concave up everywhere, or at just c you guarantee? At just c only you guarantee, right? At just c you guarantee. Later whatever is happening you don't know, right? Later whatever is happening, at c you are saying it is concave up, which means that at c the function will be something like this. I mean, some part of this, okay, maybe somewhere here, maybe somewhere here, maybe somewhere here. So which means here currently, as you can see, let's suppose if I say this is the first choice, second choice, and third choice, then currently at c it is concave up. Then if you just tell me that which kind of behavior it is, then can you just point out first or second or third? Then what is this? This is the first behavior, right? So here I'm saying it is concave up, and it is like if you just try to complete this, then it will be something like this, right? It is concave up, and this portion, I'm in this portion currently, right? I'm in this portion. So see, what I'm saying here is that this is some random function f, okay, and at c I calculated that f double c is greater than 0. Then at c it must be either be looking like this or this, right? Or maybe at the bottom, maybe somewhere flat or something like this. So basically at c it will be concave up. That's what I'm saying. समझ में आ रहा है थोड़ा कि what I'm trying to say? So at this particular point it is concave up, means that you, if you try to complete this at this particular point, then it is actually behaving like a concave up. Okay, maybe I'm not saying the function is concave up, like the complete fx might be behaving anything, but at this particular c थोड़ा सा ऐसे tilted होगा. At this particular c it is like concave up. Okay, at this particular c maybe it is behaving somewhere here, something like this or something like this, right? Now if you want to confirm that it is like first, second or third, then how you can confirm? You will be checking f dash x. Now here if I say, see, let's suppose that f double dash c or f double dash x, okay, at certain point is greater than 0. If I'm saying something like this, then what does this mean? It certainly mean that it is concave up, right? One second. Okay, it certainly mean it is concave up. Now, if I just ask you, my function that c particular c, I mean that particular value could be behaving something like this, or something like this. So if I just ask you that what is the like in what kind of structure it might be at c, then what you will be saying that okay, can you also tell me f dash x? If f dash x is also greater than 0, that means the function is increasing and concave up, which means this is the portion I'm talking about, isn't it? If f dash x is also greater than 0, then it means this is the portion I'm talking about, right? So this is the portion where, I mean, if I just tell you that f double dash c is greater than 0 and f dash c is also greater than 0, then you will say it is concave up, and it is increasing, right? So which means you're talking about this area. I hope you understood. Okay. So now if I just say, let's suppose that the function is decreasing. Okay. I mean, let's suppose if I say that this is the situation, then it means it is in this area. You're talking about this area, which means the function, if you are saying that f double dash c is greater than 0 and f dash c is also greater than 0, it means it is concave up. Yeah. Concave up, and it is increasing also. Similarly, if I just say that, let's suppose that you have something like this, then which area you're talking about? F dash x is equal to 0. Then you are saying it is concave up. F double dash x is greater than 0. And this f dash, okay, f dash c, let me write c. Okay, so this f dash c is greater than 0, f double dash c is greater than 0, and f dash c is equal to 0, which means it is actually this point, right? Have you understood? Neither increasing nor decreasing. It is actually stationary. Have you understood what do I mean by these three cases? See, greater than 0 means that I mean f double dash is greater than 0 means that it is definitely concave up. And then if I just give you one more information, which is about the f dash x also, then you can infer it, which area I'm talking about, right? Either the left side, right side, or maybe the bottom. And that is given by f dash x also. So similarly, if I say that what about if I just ask you what about this f double dash x less than 0, then you will say it is concave down, right? Which means something like this. You will say it is something like this. And now if I just give you the additional information, okay, suppose if I give you the additional information, which is saying that f dash x is greater than 0, then which area I'm talking about? Left, up, or right? Function is increasing, right? So I think I'm talking about this particular area. So my c will be in this particular area. So basically you will say that here in this area, f double dash c is less than 0, and f double dash x, sorry, f double dash c, f dash c is greater than 0, right? Why? Because here in this area it is concave down, here in this area it is increasing. Okay. Now, if I say that this is the function I have, which means f double dash x is less than 0, and if I give you the additional information where f dash x is also less than 0, then I'm talking about this. The function is here in this area, f double dash c is less than 0, f dash c is also less than 0, which means concave down and decreasing. Now, at last, if I just give you that, okay, f dash c is equal to 0, then what you will say? This is the area I'm talking about, right? This is the area. Yes, the middle one. I hope you understood. Now, let's just move to the second derivative test. Okay, this was just a revision. Now, suppose I say that uh, I give you information where I say that f dash c or f dash x is equal to 0. Then what you will conclude? then it means that it could be one of the critical point, maybe the local minima or maximum or something like this. But if I just also give you the information, if I also give you the information and also give you the information which is basically f double dash x is, let's suppose, less than 0, then what you will say, that f double dash x less than 0, which means it should be at one of this point. Less than 0 means the c I'm talking about, it should be one of this point. And then I give you the information which is f dash x is equal to 0, then you are certain that c is this particular point, isn't it? Then what does this mean? This is local maxima, isn't it? Yeah. So basically, if I give you these two information, which means I say f dash x is equal to 0 and f double dash x is less than 0, then I will say it is the maximum. Right? Okay. And similarly, if I give you some information, something like this, f double dash x is greater than 0, then you will say that it is concave up. It is concave up. Right? And since like because of this means concave up. And I'm also saying f dash x is equal to 0, which means you're talking about this point. It means it is local minima, right? But suppose I say that f dash x is equal to 0 and f double dash x is also 0. F dash x is equal to 0 and f double dash x is also equal to 0. Then actually it means you can't, like this test is not concluding anything, right? You can't say anything using this test. So basically, I will say just prefer the first derivative test. Do you remember what is the first derivative test? It is just finding f dash x and drawing on the number line, like on the roots of f dash x, whether it is from increasing to decreasing or something like that. So it is the best way to do it. But if you want, like, I mean, just for the sake of completion, we can cover the second derivative test also. But the second derivative test is not conclusive sometimes. If let's suppose f dash x is 0 and f double dash x is also 0, then you can't conclude anything. So you have 3 points here in the second derivative test, right? Let me just write those 3 points. You will say that first point is that you will say that if f dash x is equal to 0 and f double dash x is less than 0, this is the second point. F dash x equal to 0 and f double dash x greater than 0. Third point is f dash x equal to 0, f double dash x is also equal to 0. So here it is local maxima or minima? I think maxima, right? Less than 0, concave down. Okay, minima. Sorry. Mm-hmm. Uh, yeah, it is right, right? It should be minima. Concave down, right? Okay. This is correct or something is wrong? Hmm. F dash x less than 0 means f double dash x less than 0 means what? Can you tell me? Concave up or concave down? Concave down, right? So this is concave down, and that's why you have the maxima here. So this is local minima. This is can't say. Okay, I hope you understood. Now let's just do some examples. Okay, let's see this paragraph, what they're saying. How do we determine if a function has local minimum or maximum? So let's just read this paragraph. I forgot the university name, but yeah, that's fine. So what they're saying, how do we determine if the function has local minimum maximum? So first we compute the critical points. Then we can either use first or second derivative test. The first derivative test says that if the sign of the first derivative changes from positive to negative, we have the local maximum, or the negative to positive, then we have the local minimum. If there is no sign change, then we do not have any, neither local minimum or maximum, right? From the second derivative test, you can say if this f dash c is equal to 0, then we check f double dash c. If the value is positive, then c is local minimum. Minimum occurs. Negative, then c is where the local maximum occurs, right? Okay. Have you understood this? Cool. Now let's just see some examples. So they are saying find all the extremum of this particular function. So what you can do, you can either use the first derivative test or you can use the second derivative test. So first derivative test means you find the f dash x, you equate it to 0. So maybe I have the solution, right? You find the f dash x, you equate it to 0. So minus 1 and 2, these are the two solutions that you are getting. So if you find the f dash x, you equate it to 0, then you are getting x equal to minus 1 comma 2, right? So these are the two values you are getting. Is this fine to everyone? Okay. Okay. Now, what you can do, you can either apply the first derivative test or the second derivative test. So how to apply the first derivative test? Basically, you just need to put this is minus 1, 2, and then you can check whether the sign are changing from positive to negative or like that. So using the first derivative test, you have minus 1 and 2. You can find out the answer. Using the second derivative test also, you can find out the answer. So let's just see the second derivative test in this particular example. So here, f double dash x will be, it is basically, okay, sorry, I'm cheating here and there, but it is 12x minus 6. 12x minus 6. So now, if you check at x equal to minus 1, so f double dash minus 1, it is negative, right? F double dash plus 1, it is positive. So you can tell the answers whether it is maxima or minima or something like this, right? So since it is negative, it is maxima. So minus 1 is, you can say, is the maximum point. 2 is, okay, this is 2. 2 is minima. Yeah, Abhay, nothing much has been covered. Like I was just revising the second derivative test. Okay, so don't worry. So I think that is fine. Now let's just see this particular example. Can you do this particular example as a homework? Just a first and second derivative test. Okay. Okay. Now let's just see point of inflection. So I mean, here, let me first give you the definition. What is the point of inflection mathematically? So we have a point of inflection at certain point x if we satisfy both of these conditions, which is saying that f double dash x is equal to 0 and f double dash x changes its sign. Okay. Then we say that this particular point is a point of inflection point, right? So for example, yeah. So for example, let's just see this. So here, if you calculate the double derivative of this, then what it will be? The first derivative of this f dash x will be 3x squared minus 9, and the double derivative will be 6x, right? Okay. Now at x equal to 0, if you check, then f double dash 0 is 0, right? Less than 0, if you check at x equal to 0, it is 0. And at before 0, it is negative, because this 6x is obviously negative before 0. After 0, it is positive. It means that 0 is point of inflection, right? Are you getting my point? So this 0 is point of inflection here. Why? Because less than 0, it is negative or positive, whatever. Basically at 0, it is changing the sign, and at 0, it is 0. So basically what is happening here? Here you are changing the curvature. See, what does this mean? Negative means it is concave down. Before that, just before the 0. See, can I say that the function was like this? Can I definitely say? Or can I only say in the neighborhood? In the neighborhood, it was behaving like this, concave down, isn't it? In the neighborhood only we can say, right? Which means that, see, it is concave down throughout, that is fine. But if I'm checking at 0, if I'm saying f double s 0, I mean 0.1, if I'm saying 0.1, I mean somewhere here minus 0.1 and plus 0.1, if I'm talking about, then actually it means that I'm talking in the neighborhood only. At this particular point, I'm saying that it is actually concave down, right? So it is concave down at just less than 0, it is concave up just greater than 0, and at 0 it is 0. So basically this is called point of inflection, which means at this particular point, the function is changing its behavior from concave up to concave down. So just imagine one case that let's suppose the function is increasing. Okay, let's suppose the function is increasing. And then, as I said, like, I mean, this is just one special case. I will talk about this special case, but suppose the function is increasing. And at certain point it becomes flat, and then it has two options, right? It may increasing, may keep on increasing, or it may go decreasing. So let's suppose it has two options. If it is decreasing after this, it means that it is a point of maximum. Why? Because this f dash, if you talk about f dash x, it was increasing, so greater than 0. Here it was decreasing, so less than 0. So if you talk about this particular behavior, if you talk about, then you will say this particular behavior is point of maxima, right? This is the point of maxima. But let's suppose if you talk about this particular behavior, which means here also it is increasing something, I mean in between it got 0, but then again it started increasing, right? Then it is not maxima or minima, so it is basically a point of inflection. Where you are saying in between at this particular point, this f dash x is equal to 0. So before that increasing, but something happened, and after that also increasing. So this is called point of inflection. But suppose before that increasing, something happened, and which means something is this f dash x is actually 0. And then after this it started decreasing, then this is a point of maximum, right? Is this clear to everyone? Now, it is actually not necessary that at the point of inflection you have basically this f dash x equal to 0. This is just one case. So this is point of inflection, that I agree, but this is just a one case of point of inflection where the f dash x is actually 0. Mathematically, we only have this thing. It doesn't say anything about f dash x, which means f double dash x should be 0 and it should be changing the sign. This is the definition of point of inflection. What about f dash x? What about f dash x? It may be 0, it may not be 0. Okay. So can it happen that f dash x equal to 0, but f double dash x is not 0? Can it happen? Like, I'm asking in general. I think it can happen, right? So f dash x is, let's suppose 2x. At x equal to 0, it will be 0, and at double dash x, it is 2. So I think it can happen. Okay. Just asking a random question. Cool. So what I'm saying here, that if someone asks you the point of inflection, then this is the definition of point of inflection, where the f double dash x is 0 and f double dash x should also be changing its sign. What about the f dash x? F dash x could be anything. Okay, I will give you the examples, but first I'm giving you the theoretical definitions. What about if f double dash x is 0, but it doesn't change its sign? Maybe let's suppose if you talk about the example of x power some higher power. Okay, if it doesn't change its sign, let's suppose x power 100. If you just Google out graph for, just Google Google this graph for x power 100. Just Google this out, and can you give me the graph? How does it look like? Can anyone do this? Okay. So if you talk about the graph for, let's suppose, x power 100, then most probably it should be something like this. I mean, should be very, very flat here. Okay, around the zero. Around the zero. So basically, if you check x power 100, x power 100, or maybe 101. Okay. I mean, let's talk about the 101. Can you give me the graph for x power 101? Just a second. It is something else. Okay. So basically what I'm saying here, like if you have some graph, let's suppose x power 100 or something, and if you take some point in this region, okay, just before zero or maybe just after zero, actually it is very much flat. This graph must be very much flat because around the zero it is almost zero, right? So at this point, if you check f double dash x, then it is almost zero. And before that also it is almost zero. After that also, basically it is not even changing its sign. So these points are not point of inflection. That's what I'm saying. Okay. So yeah, it is x power 101. Anyway, what I'm saying, that if your function, okay, maybe I need to look at the function, some example of this. So what I'm saying, that if your function does not change its sign, then also it is not a point of inflection. So basically both of these conditions must be true. And this is what point of inflection is. So if someone asks you, what about that f dash x sign? It could be, I mean, what about the f dash x? Could be zero, could be not zero, could be positive, could be negative, anything. Okay. What about the f double dash x? F double dash x must be zero. Cool. Now let's just see some example. Suppose I have this, and then they are saying find out all the point of inflections. Can you do this? Can you find out all the point of inflections? So basically, if you just find out the double derivative of this, then it will be, single derivative will be 3x squared, double derivative will be 6x, right? So what is the point of inflection here? You put it 0, and then check if f double dash x is changing its sign or not, before 0 and after 0. Since it is changing its sign, that's why you will say that this particular function is, this particular point is point of inflection. Why? Because f double dash x is 0 and changing the sign. What about f dash x here? F dash x equal to 0, right? This is by coincidence. Now, maybe let's just see this example. So see, sorry, f double dash x is actually not 0. Okay, this is not 0. Actually, it doesn't matter whether it is 0 or not, but yeah, this is not 0. And like it is 0 not, actually this f dash x does not matter. So f dash x here is not 0, right? In this particular example, as you have seen, that f dash x is not 0. Okay, so these two must be true. Let's just see the explanation. So this is f dash x, this is f double dash x. This means there are no stationary point, but there is a possible point of inflection at x equal to 0. So here it is changing the sign. Since it is changing the sign, it is a point of inflection, right? So let's just see this particular example. So here, if you see at x equal to 0, this f dash x is not 0, but f double dash x is 0, and it is changing the sign. Changing the sign means it was concave down, and from the concave down, it is going to concave up, right? So Aditya is asking, sir, f double s x sign changes should be sufficient. How did we changing the sign without being zero? Maybe due to continuity, right? Maybe the function should be continuous or something. It might relate to that. I need to just look at this. Maybe because of the continuity, we need to put that condition. And what could be the some other reason? Maybe like I need to look at this. Maybe some other reason also. Some limiting cases also could be there. Right? Could be minus infinity to plus infinity. You can say. I mean, before that, the function, like I'm just plotting the graph of f double dash x. So could be something like this. I mean, it is reaching to minus infinity, f double dash x, and plus infinity, and here minus infinity. I mean, what I'm saying that, okay, I mean, around this zero, it is before zero, it is negative. After zero, it is positive or something like that, or negative, positive, whatever. And and then at zero, maybe it is not zero, right? At zero, it is something else. So maybe something like that. So basically, these two conditions must be true. That's what I'm saying. Okay. Without f double dash x equal to zero, how to find the point of inflection? Yeah, that's what I'm saying. That f double dash x must be zero to find the point of inflection. Yes, true. So let's just see this example. And if they ask you to find the point of inflections, then what you will do? You will make f double dash x at zero, and you will check whether the signs are changing or not. So if you do this, f double dash x equal to zero, then it is x equal to 1, and x equal to 1 sign is changing. This confirm that that x equal to 1 is a point of inflection. Okay, if you can see this, see here, this confirm that that x equal to 1 is a point of inflection, right? Okay. Now if you check that f double dash x is actually zero, changes the sign and changes the sign. These things are fine, but can you check what about f dash x? F dash x was 3 into x minus 1 whole square. Can you tell me whether the f dash x is zero or not? So f dash x is zero. Does this tell you anything? So it is just a coincidence, right? Now f dash x could be zero or not, but I should be satisfying these two things. So see here what is happening at 1, it is actually like becoming stationary at 1, right? So it is becoming stationary. Okay, in this example, in this example, it is not becoming stationary. Yeah, that is good point to compare, I think. So basically, we have seen two examples. Here, the f dash x, so this is a graph of x cube plus x. Here, the f dash x was positive, right? F dash x was how much? Do you remember? If you differentiate it, it will be 1. So f dash x is actually positive. Right? So I can write here. So this was one example. This is the point of inflection. This is the point of inflection. Here the f dash x is not zero, right? And this is the point of inflection where the f dash x is also zero. So anyway, like I'm just telling you that f dash x does not matter to us. Here the f dash x equal to zero at point of inflection. Okay. So basically, at point of inflection, you might be having the stationary point, which means a curve might be flat or curve might not be flat, right? Curve might not be flat. It is changing so smoothly that it is not even flat. Okay, and immediately it's changing its value. But it could go flat for some time. That could also happen. So basically, the point of its inflection itself, you can say, I mean, these are the ordinary point of inflection where the flat is not the curve is not flat, but you can say these are of two types. One is stationary point of inflection where the curve become flat also. Okay, so the curve could be flat at the point of inflection, could not be flat. So these are the two examples. This is the ordinary point of inflection, If you want, you can call it the stationary point of inflection. Is this clear to everyone? And we have seen both the examples also, right? Okay. Now let's see this question. This question I have taken from some university. So let's see this question, what they are saying. The following table gives you the values of a continuous differential function f dash, the derivative of f. So they are giving you the values of f dash x. Okay. And then they're asking you something. So can you solve this question? So they are giving you the values of f dash x, and then they're asking you something, right? So they are saying that the function f has a local minimum where x equal to this. So at which points the function will be having the minimum? That's what they're asking. Maybe I can copy this on the next page and just zoom it a little bit. So, okay. So let's just see this particular question. At which point function is having local minimum? Can you tell me? Wherever it is going from decreasing to increasing, the f dash x. F dash x is going from negative to positive. So negative to positive, it is going at between 2 to 3 it is going. I mean, between 2 to 3, you can say between x equal to 2 and x equal to 3. Between 2 to 3, it is going from negative to positive. Is this okay to everyone? Minimum, right? So decreasing and increasing. I hope 2 to 3 should be fine, right? Or I'm doing something wrong. F dash x should be negative, I think, and then it should be positive. So, yeah. Okay. Okay. Let's just see the answer maybe. Yeah, 2 to 3 is the correct answer. Okay. And let's see the next question, what they're asking. The function f has a local maximum. So you can find out the local maximum also, right? So what about the local maximum? This is from positive to negative, right? Function increasing and decreasing. So -1 and 0. Okay. Let's see this interesting question where they're saying the function f has an inflection point, between which value to which value. There is one more answer possible. So there are two answers possible. It has an inflection point between which value to which value. So inflection point means what? As I told you that f double dash x should be 0, and before that f double dash x, and I mean f double dash x should be changing its sign. Yeah, f double x. So what do you think at between which point to which point f double dash x is changing its sign? F double dash x will change its sign. This is nice question, right? Okay. When does f dash x change its sign? Whenever fx is increasing to decreasing behavior, something like that, right? I mean, decreasing to increase. Whenever fx has some behavior like increasing to decreasing or decreasing to increasing, something like that. When f double dash x will change its sign? Whenever f dash x is showing some behavior, it is increasing and then it started decreasing. Wow. So which means it was increasing and then between -3 to -2, it started decreasing. So between -3 to -2, there could be a point of inflection. Why? Because see, I need to check whether f double dash x is changing its sign or not. So f double dash x, see, you need to relate it to with the f dash x. Just tell me when does f dash x change its sign? Whenever the function is going from either increasing to decreasing or decreasing to increasing, right? So maybe like function is going from increasing to decreasing or decreasing to increasing, something like this, right? Now function means f is going from increasing to decreasing or decreasing to increasing. Now I want to check when f double dash x is changing its sign. Whenever if I just put the f double dash x here, f double dash x, then you will say whenever f dash x is going from increasing to decreasing or decreasing to increasing. So let's just see. So here f dash x is increasing, and then maybe at certain point between -3 to -2 it started decreasing, and that's why it is minus, like it is lesser, right? That's why it is lesser. So between -3 to -2 possibly, and then it is decreasing. Okay, see yahan tak decreasing hai, theek hai, and then decreasing, then again decreasing. Okay, then between 1 to 2 it started increasing, right? Between 1 to 2 it started increasing. So maybe -3 to -2 and between 1 to 2, right? Is this okay to everyone? So these could be 2 point of inflection. Now, yes, I need to check that whether the f double dash x is 0 or not. Like we have only checked one of the condition, but I need to check whether the f double dash x is 0 or not. So see, any function f double dash x could be any function. It is basically, there is a point where I mean between -3 to -2 there is a point. Whatever this point is, it is, let's suppose, negative, and then this is positive, right? So from negative, I mean the value was negative and then it is positive. So somewhere it has to be equal to 0, right? It has to be equal to 0. I mean, without it, it is not possible. Like the function, if the function is continuous, it has to be equal to 0. So that's what the Rolle's, I think, yeah, Rolle's theorem or intermediate value theorem, right? So that's what the intermediate value theorem says. So we will see this later. So yes, someone, I think Aditya has suggested that why we are having the second condition that f dash x equal 0. So I think you're right. Like because of intermediate value theorem, you can say that this first condition is redundant, but here you have to put that function is also continuous. So if I'm not putting the condition this function is continuous, then it is fine to say that f double dash x is equal to 0 and it changes its sign. Okay, anyway, let's not worry about these things. I hope a little bit you have got, but anyway, let's not worry about this. Okay, so by the way, have you got what I'm saying here? The first condition that f double dash x equal to 0 is kind of redundant if the function is continuous, right? Because it can't go, if some any value, it can't go from negative to positive all of the sudden, like all of the sudden without hitting the 0. It has to hit the 0, and that's what the intermediate value theorem says. That's what we will see. Okay, so that's what I was saying. When Aditya asked, then I was saying the same thing, that yes, the function, maybe because of the continuity we are putting this. That was my intuition, but yeah, that is correct intuition, I think. Okay, cool. So -4 to -2 and 0 to 2. Yeah, our answers are also correct, I think. -3 to -2. We are giving little precise answer, right? We are saying -4 to -2. Increasing. Yeah, I think this is also correct. Till -3, it was increasing, and then yeah, it was increasing, and then from -3 to -2, there will be some point, right? In between -3 to -2, there will be some point. So like we have given little precise answer, but if you want, you can put it -4 to -2 also. Okay, I mean, doesn't matter. We have given little more precise answer. -3 can be inflection point. Okay. It is increasing. Yes, right. And at -3 itself, it might have started decreasing suddenly, right? Yes. Yes, that is true. So -3 itself could be the inflection point, because at -3 itself it could start decreasing all of the sudden. So if I need to talk about in between, anyway, like these are the small points. So it doesn't matter, like they will not test you that much in calculus, but still we are just seeing the possibility. It is -4 to, it is better to say -4 to -2 and 0 to 2. Okay. By the way, like the examples are just for you to get the idea of inflection point and all. Okay. So I hope you are getting the idea here. So that's why I picked these examples, just to get you the good idea of these things. Okay. Now let's just see few theorems which are like intermediate value theorem or Rolle's theorem, or there is one more theorem which is called Lagrange mean value theorem. So let's just see this theorem, which is first theorem, which is intermediate value theorem. So what does it say is that if there is a continuous function and on a closed interval AB it is a continuous, then if D is in between FA to FB, then there is a number C such that F equal to D. So maybe I have already the diagram. We have already covered this. So I can differentiability. Okay. No. So it should be in the intermediate value theorem. So let's just see this. So what they're saying, if f is a continuous function and in between a to b and fa and fb, like there is a point D, then you must be having C such that f is equal to D. Obviously, right? I mean, if you draw a line, have you understood this in the videos? If you draw a line on D, then it must be, there must be some C. It must be cutting, right? The function. There must be some C, which means what I'm saying, that if you have something like this, right? Where this is FA. Okay. This is, let's suppose, FB. And then you are having any point D. Then there must be C. This is A. This is B. There must be C in between A and B such that that is FC equal to D, right? There must be C. And that's very obvious from the diagram itself. If this function is continuous, then it must like this D must be passing through the no, cutting the curve at certain point. Okay, cool. So that's what this theorem says. But this theorem we will be using for some other purpose. And what is that purpose? We will be saying that if FA into FB is less than 0, which means that FA and FB are having opposite signs, which means this is A. Okay, I mean, this is what FA is, and let's suppose this is what FB is. So FA and FB are having opposite signs, either this thing or maybe FA is positive and FB is negative, something like this. Okay, so let's suppose this is A, this is B. If FA and FB are having opposite signs, then it must be cutting somewhere the x-axis, which means then you can say there exists a C such that FC equal to 0, right? Can there exist multiple C's? Yes, there can also exist multiple C's. Okay, because it can go something like this. It can go something like this. There can exist multiple C. So I can say there exist at least one C. And that's what the theorem says, right? There is a number C. I mean, there is at least one number C that satisfies this. So maybe we can directly have the questions here. So let's suppose we want to prove that this function has a root between this -2 and 2. So can you prove this? This is continuous because this is a polynomial function and polynomial functions are continuous. Then if you check f of -2, it will be 16 minus 8. It is, I think, greater than 0. Okay. Sorry. Yeah. I mean, f of -2 is greater than 0, but I don't think it will help. So can you solve this question? So they're asking, it has a root in this interval. So see, f of 0, if you check f of 0, then it is negative -4. F of 2, then it is 16 minus 6. It is 10. So it means there is a root between 0 to 2. There is a root between 0 to 2. So it means there is a root between -2 and 2 also. And similarly, you can say that I think there is one more root, right? F of -2 is also positive, I think, right? 16 plus 2, 18 minus 4. I think this is also 14, right? So similarly, you can say there is one more root between between minus 2 and 0. So at least 2 root you can guarantee by just the observation. Is this okay to everyone? Yeah, at least 2 roots in between minus 2 and 2. Okay. Cool. So I hope that is fine to everyone. Now let's just see this question, which I have taken from University of Texas. Consider the function fx, which is defined to be 0 if x is equal to 0, which means it is 0 if x is less than or equal to 0. It is 1 if x is greater than 0. This is something like this, okay? Which means, like, I think till this point it is 0, and then till 0 it is 0, and then it suddenly become 1, something like this. Okay. Now what they're saying, why doesn't this contact? So they are saying f of minus 1 is 0 and f of 2 is 1, right? So never takes the value 0.5. So which means, let's see, f of 0, f of minus 1 is 0, f of 2 is 1. Now what does this intermediate value theorem says? You take any value between this f of a and f of b. Let's suppose you take the value 0.5. So there must exist some constant which is actually equal to 0.5, right? This is what intermediate value theorem says. But actually this is not true for this function. Why that is the case? There is no value c such that it is 0.5 because it is not contiguous. Yes. So it is not true for given function. Given function. And intermediate value theorem is not applicable. Because function is not continuous in this range. Okay, function is not continuous, that's why this is happening. So this is the answer here. Function is not continuous. Let's just see this question. So what they're saying, the equation x power 7 plus x minus 1 equal to 0 has a solution in 0 to 1. Maybe you can do this at your home, right, as an homework. That is easy question. I have the solution on the next page. Okay, so you can do this also as an homework. Okay, I have the solution on the next page. Now let's just see the Rolle's theorem, and maybe I can quickly revise you the questions I had in the video. So I think these were the easy questions only. Yeah, this question was nice. There was one question. Yeah, the counter example, this was nice, right? So they are saying that if they are having the opposite sign, sorry, this false by the ring. If fx is, yeah, if fx is having a root in between a to b, then they must be having the opposite sign. So it is not true. I mean, the converse of this statement is not true. Why? Because of this kind of case. Okay. So have you seen this question? You might not be able to recall currently, but yeah, converse of this statement is not true, which means if they are having opposite sign, that must be passing through 0. But if they are having a root, then it doesn't mean they are having opposite signs, because that they might be they might come back and they might be having the same sign. So I can say, can I say, maybe like I'm just guessing it, if they are having the same sign and then they are having a root, then there must be at least 2 roots if the function is continuous, right? I mean, they must be hitting at least 2 times. And if they're having the opposite sign, then there must be at least, I mean, the number of roots will be odd, basically. Number of roots will be odd because it might go down again. Number of roots will be odd or even. You can conclude something like this, right? I mean, I need to check it, but using the intuition, I can say that if FA and FB are having opposite sign, I think that's true. and obviously, and f x is continuous in A to B, then what you will say? Number of roots are odd, right? Which means you either be having, so if they're having an opposite sign, then something like this, you either be having one root or you might be having more than one root. So something like this, right? Opposite sign, again opposite sign. So here negative, here positive. So it is the three roots, 1, 2, and 3. It is just one root. Okay. And then similarly, you can say that if they are having a same sign, then number of roots equal to even. Yes, yes, right. It could be a quiz question. Don't worry, we will see something else for the quiz. कुछ इंतजाम करते हैं, right? So a number of roots will be even here. So which means if they are having the same sign, so either two roots, maybe more than two roots, right? I mean, but it has to be even. 1, 2, 3, and 4. Okay. Now let's just see this Rolle's theorem. So this theorem is very intuitive also. This says that if you have 2 points where f and fb both are same, the function is continuous, right? Then continuous and differentiable, then there is a number c such that f dash c is equal to 0, which means they are saying that if we are having f and fb same, which means you are having fa here and fb also same. So which means that the fb is, I mean, it is returning to the same value. So fa and fb both are same, then there must be some c such that this f dash c is equal to 0, right? So maybe something like this, or maybe something like this. So you can say that here this is A, this is B. See why I'm doing this. I mean this in little hurry, because that is already there in the in the videos, right? So you can say like here the multiple C's are there, right? Multiple C's are there. So here f dash C is equal to 0 for multiple points, right? Okay. Okay. Now let's just see this particular question. So they are saying f3 is equal to 2, f dash 3 is equal to 1 by 2, f dash x is greater than 0, f double dash x is less than 0. Okay. How many possible roots this f has? Maybe let me just solve little easier questions first. I don't know if it is easy or not easy, but let me first solve these kind of questions, or maybe we can solve this first. So can you try solving this? f3 is 2, f dash 3 is 1 by 2. Function is always increasing. For all x, they are saying it is always increasing. Function is always increasing. Okay. At 3, it is 2. Okay, this is f dash 3. Okay. At 3, it is 2. It is always increasing. They are asking how many roots does this f has. And then function is, yeah, this is a good question, right? Function is concave down. Function is always concave down, right? Okay, that's really a nice question. Do you want to solve this? So what they're saying, function is always concave down, not at just one point. They're saying for all x, it is concave down. If the function is concave down and function is always increasing, then I think they are talking about this particular area, right? Function is always increasing. They are always talking about this particular area. How many roots this f has? If the function is always increasing, then which means that they are saying that the other possibility does not exist. Then it can have at most one root, right? It can have at most one root. But the only thing is to prove whether it is or at most one or exactly one. That's what we need to prove, right? See, the function is always increasing. That's the point. Yeah, it should be exactly one. Why that is the case? See, this is the area in which we are, right? So the function should be something like this only, something like this, always something like this. This is the area in which we are. The function is always something like this. Maybe it is a graph of log x or something like this, right? So basically, like I mean, you can argue by looking at the geometrical interpretation, or you can argue with the mathematical interpretation also. You are saying that f3 is 2, and since the function is always increasing, can you tell me it is strictly increasing? Remember, can you tell me what is f3 minus, which means just before 3? It will be 2 minus, I mean, just less than 2, because it is always increasing. Remember, okay. See, if f3 is 2, then before 3, it must be lesser than 2. Must be lesser than 2, isn't it? Is this okay to everyone? And even before that, it must be lesser than that value, or even before that, it must be lesser than that value. So basically, somewhere it will, like this f is 0 also, right? Somewhere f is 0 also. Because it is always increasing. So if you go in the reverse direction, if you just look at the reverse direction, I mean, see, this is f of 3, but there must be some fc where it is 0, क्योंकि 0 से ही 2 आया होगा ना, बूंद बूंद करके भी तो घड़ा भरा होगा, मतलब कहीं ना कहीं that must be 0, because it is always increasing, and it is somewhere it is negative also, somewhere it is negative also. Basically the function is something like this, क्योंकि नेगेटिव से 0 आया होगा, 0 से 2 आया होगा, क्योंकि इंक्रीजिंग है, द फंक्शन इज ऑलवेज इंक्रीजिंग. दैट्स द प्रॉब्लम, आई मीन दैट्स द पॉइंट, right? So let's see the explanation that they have. The function have at most one root. Okay, so first they are saying it has at most one root. If it had two roots, the Rolle's theorem would mean that f dash x equal to 0 for x between okay, they are still saying at most two roots, at most one root. They are not saying exactly one root, right? But we are arguing that it is exactly one root. I mean, there is not a possibility that 0 roots exist. नहीं ठीक है, डोमेन तो मतलब, हाँ मतलब that is also okay, but domain we should be assuming the real number. It's not an issue. But I think in this case it should be मतलब exactly one root. There is not a possibility that it can have 0 roots. There is no root at all. It must be touching somewhere this x-axis, right? If somewhere it is 3 and it is always increasing, तो कहीं से तो आया होगा ना 3. It must be somewhere 0 also, according to me. Okay. Now, I hope that is fine. Now, let's just see the sketch a possible graph for f. So, as I said, like this could be the possible graph for f, where it is always increasing and it is concave down, right? This is the possible graph for f. Okay. Maybe it is a graph of log x, right? It is a graph of log x, and if you take the differentiation, it is 1 by x. So maybe you can just adjust the constant, this 1 by 2 by something like this 3. So it is 1 by 2, 3 by 2, right? So maybe it is a graph of 3 by 2 log x, because if you differentiate it, it will be 3 by 2 into 1 upon x, and then if you put x equal to 3, then it will be 1 by 2. So it is satisfying this condition. Okay, but it is not satisfying this, right? Yeah, anyway, like you can adjust the constant. Maybe you can take the two constant, maybe log x plus I mean, you can make an equation like a log x plus b, a log x plus b, and using that equation you just find out the values of a and b such that it satisfies these two things, and then we finally have the answer. Anyway, like I hope you got the point. Like the roughly the graph will be something like this, right? Something like log x. Is this okay to everyone? Okay. Now you are getting little more intuition than you already had about this calculus. So basically, especially about this part, that if these two things are given, then how to interpret this, right? Okay. Now let's just see this question. So we will be solving now questions where they will be asking about the exactly one root, about exactly one root. So do you remember how to solve these kind of questions about exactly one root? So we will be taking the help of f dash x. So what will I say? That I will say that, okay, for some value, can you tell me for some value, maybe f of maybe -5 or something. So for some value it is less than 0, maybe f of +5, it is greater than 0. So there is at least one root is guaranteed, right? At least one root that is guaranteed. But we want to check whether it is exactly one root or not. So how to check exactly one root? Do you recall this? If I just tell you Rolle's theorem, no, sorry. Okay, Rolle's theorem notes I don't have. Okay, not an issue. No problem. So do you recall that how to check? Yeah, using the f plus x. So at least one root is there, but using the f plus x, you can check that whether it is exactly one root or not. So f plus x will be 2 plus e power x. Since it is always greater than 0, function is always increasing. Since the function is always increasing, you cannot cut down, you cannot come back, right? You cannot decrease. So exactly one root. Okay, it is at least one root, and then that's how we solve it. So for the exactly one root, we take the help of f dash x. Okay, so we take the help of f dash x for exactly one root. I hope that is clear. Now similarly, you can do this question. This is a good question you can do as an homework. You want to prove that there is exactly one root. Okay, unique root. How to prove it? Using the f dash x. The solution is on the next page, don't worry. So you can easily do this question. Okay, trust me. Now let's just go here. This is little good question where they are saying that you have a function and it has a 0 between x of -1 and 1. Okay, so basically show that you want to show that this function has a root between -1 and 1. Can you show? And then they are saying, be careful. This function is not continuous at this 0. So function is not continuous in this range. If this is continuous, then I think you can easily prove it, right? At 1, it is greater than 0. At -1, okay, at -1 also it is greater than 0, right? Sorry, it is 1 upon e -1. No, at -1 it is less than 0. And at -1 it is less than 0. At 1 it is greater than 0. So if it is continuous, then you can do it. You do using the Rolle's theorem. But it is not continuous. But still, can you play some trick? That's what they are saying. You are getting my point? What is the question here? If this is continuous, then you could have done using the Rolle's theorem, but here it is not continuous. So what to do? Okay, I also don't know. Let's just see. It is negative. See, at -1, it is less than 0. That I completely agree. At 0, it is not defined. That I also completely agree. But 0 से just पहले क्या होगा? This is here negative. 0 से just पहले, I think this is a huge number, minus infinity, right? 0 से just पहले here minus infinity. Okay. 0 से after, just after 0 it is plus infinity. Then it is dropping the value negative to positive. It is changing from negative to positive in between -1 and just before the 0. This is 1 upon x square. If I increase the x, do you have any idea? Value check करेंगे, -1 से 0. Okay. If I increase the x here, I mean, this is x square. So 0.5 is actually lesser value, right? This will decrease. This will keep on more decreasing. Okay. This will decrease. And since this is 1 upon e power x, and I'm putting the value, let's suppose -1, 1 up, okay, 1, and then if I put 0, it is increasing, it is decreasing. Okay. Have you got some idea? Let's just see the solution. I think we need to check some values here and there. So let's just check the solution. So they're saying, note that f0 is not defined, f is continuous. Continuous everywhere, everywhere it is defined. Okay, except 0, it is continuous everywhere. But the intermediate value theorem requires f defined on the entire interval, else it can still jump. Okay, anyway, we have f -1 less than 0, f1 greater than 0. Note that limit x tends to 0, okay, minus infinity. So just a second, x tends to 0, which means, okay, here also it is minus infinity. Is this? If you put something greater than 0, so it is minus. Yeah, sorry, I did this wrong. So here also it is minus infinity. Yeah. Okay, तब तो हो गया ना, फिर क्या दिक्कत है? So you can take the range which is 0 to 1, right? You can take the range which is 0 to 1. So it is negative, and at 1 it is positive. So you can say that that it is continuous between any value. You can say 0, 0, 0, 0, something like this, right? And then 1. It is continuous between this interval. So there must exist one root. Okay. So something 0.01 you can take, and there must exist some root. Okay, cool. Sorry, I did this wrong. So it should be minus infinity only. Because they are saying limit exist. Because it is x tends to 0, they are saying it is minus infinity. Either you go from the positive end or you go from the negative end. So that's what it is given to us. That the limit exists. Yeah, yes. Okay. Now let's just see this mean value theorem. Okay. So this is also known as first mean value theorem, or it is also known as Lagrange mean value theorem. So either you call it a first mean value theorem, Lagrange mean value theorem, or just mean value theorem. First mean value theorem, maybe because it is involving the first derivative. Okay. So it will involve the first derivative. That's why probably it is called first mean value theorem. Cool. Let's just see this. So, so what does this mean value theorem says? That suppose f is continuous on a to b and differentiable on a to b, then there is a number c such that this happens. So what they're saying, that if it is continuous and differentiable between a to b, let's suppose this is a, this is fa, and there is some value b, and this will be fb. Okay. And then they are saying, if it is continuous and differentiable in this particular interval, now you can have any function, something like this. Then there must be a point C such that there will be a line joining these 2 points, isn't it? What is the slope of this line? What is the slope of this line? Whatever is written here, right? The slope of this line is FB minus FA upon B upon A, B minus A. This is the slope of this line. Now what they're saying, that if you take the slope of this line, I mean the slope, the line that you're talking about, which is this, if you take this line, and if you take a tangent on some C in between, okay, maybe the function is something like this, then tangent on some C, maybe here, then this tangent at some C is parallel to, so this is the slope at C, this is the slope of the line joining A and B, right? These two are different slopes. So they are saying if you are taking some point C in between A and B, then at the point this, I mean, there exists a point where this slope at this point and slope of the line joining A and B both are same. So what I'm saying, let me go to the next page. Suppose you have something like this. This is A, this is B, right? And then, sorry, let me draw something like this. Yeah. Suppose this is the function that you have. And then I say, you draw a line, which is joining A and B, something like this. There will be a slope of this line. Then they're saying there exists a point C such that the slope on that point, and these two lines are parallel actually. The line which is joining A and B and the tangent at C are parallel. So that's what they're saying. Okay. Okay. So they are saying the tangent at C and the line joining A and B are parallel. So there exists a point C. Cool. So basically, mathematically, the equation is something like this, that if you have A and like a function which is continuous between A and B, then this exists. There is a point C such that f dash C equal to FB minus FA upon B minus A. So I'm just trying to understand this intuitively. Okay. Suppose that actually I'm not sure if I can frame an example here, but let me just try to give you an example. Suppose you are going from a place to another place, okay, and suppose the distance between these two places are is something, let's suppose the distance is 100 kilometers, and if I give you the time that you have reached in 4 hours, okay, then can you tell me the average speed? So basically, this is, let's suppose, a point 0, a coordinate 0 or something, or this is 100. So you will say the average speed was 100, and whatever the relative distance I'm taking, 100 minus 0 upon 4 hours, right? It is basically 25 kilometers per hour. Kilometer per hour, isn't it? You will say that this is the average speed. I mean, on average, you have taken this thing. Is this okay to everyone? So what I'm saying that this speed is average, like you have 100, you have covered 100 kilometers in 4 hours. It means on average you are running, I mean, if you run with the constant speed of 25 kilometer per hour, then I think you should be reaching in 4 hours this 100 kilometers. Okay. And what is this f dash c? This f dash c is speed. So if I just measure this f as a distance, then this f dash c is basically speed at c. So basically they are saying that your average speed, whatever is your average speed, I mean, there must be a point where, see, if you're running at 25 kilometer per hour, then tell me, are you always running 25 kilometer per hour, or sometimes less, sometimes greater? Sometimes less, sometimes greater, right? So there is a point C where you will be exactly matching this 25 kilometer per hour. which means sometimes you are running with the lesser speed, sometimes maybe more speed, but there is a point C such that this f dash C is exactly equal to this average speed. So basically, this is also called as average slope. Average slope. I mean, there are slopes at every point, but if you take the average of all of these slopes, then you will be getting FB minus FA upon B minus A. This is the average slope. So, I mean, intuitively you can understand like this, that there is an average slope, I mean the slope here. And if you find out the slopes at every point, then there must be a point where uh, at that point the slope is exactly equal to the average slope. Yeah. So basically something like that you can understand, like you don't need to worry about it much. But yeah, I just tried some intuition. Actually, like in the gate they don't ask these things much, so that's why I don't want to spend much time. So maybe we can directly see some questions and you will get to understand that where to apply this particular theorem. So let's see this question. What they're saying: there exists a differentiable function fx such that f dash x is less than 1 and f0 is 0 and f2 is 2. Okay, just a second. I will come to this question in a while. Maybe I can do this question first. So what they're saying, like by applying the first mean value theorem, or they also call it mean value theorem, or they also call it Lagrange theorem. They are saying by applying the first mean value theorem to root x, show that for each positive integer n, this happens for some c between n to n minus 1. See, what is this mean value theorem says? That in between a to b, if your function is continuous, then you have f dash c and differentiable basically. F dash c equal to fb minus fa upon b minus a. Right? Now, here they are saying this root x. So what is this f dash x? I think it will be. Can anyone tell me quickly? 1 upon minus 1 upon 2 root x. Sorry, 1 upon 2 root x. This will be 1 upon 2 root x, right? Okay. Now what they are saying, that there is a certain point c such that 1 upon 2 root c, 1 upon 2 root c is exactly equal to fb, which is root of n plus 1 minus root n upon n plus 1 minus n. So they are saying there is at least one point c such that this happens. So you are just applying this theorem, right? And then you can prove this particular statement by using the theorem. So by applying the first mean value theorem, you can prove this statement. So basically, it is not always very intuitive that how we can apply this theorem, because that's where they have given the hint that apply the first mean value theorem. But do you think they really have to give you the hint? They just have to tell you that, okay, for root x, tell me that in between n plus 1 to n, this exists. So it is not always very intuitive that where to apply this first mean value theorem. But I hope you understood this particular example, that how we are solving it. Is this okay to everyone? Okay. Now let's just solve this question. And I want you to solve this question before I solve this question. So what they're saying, let f be a differentiable function with two distinct root a1 and a2 basically. Okay, a1 and a2, where a1 is less than a2. Then f dash has at least one root in a1 and a2, which means they are saying कि f के अगर दो रूट्स हैं तो f dash x must be 0. So basically f dash c, if I apply the theorem, it must be, let's suppose I'm applying between a1 and a2. So it will be a2 minus f of a1 upon a2 minus a1, isn't it? Now this a1 and a2, since these are roots of f, that means, okay, can you go from here? How to solve from here? Since these are root of f, then it means these must be equal. Right? So it is basically equal value. So it is 0 upon equal and also 0 basically, not just equal. Since they are roots, they must be 0 also, right? Okay. These are equal and 0 also. Anyway, for us, the equality itself was fine. ये तो Rolle's theorem हो गया, right? It is just like a Rolle's theorem. If f equal to, नहीं, Rolle's theorem तो नहीं. But yeah, I hope you understood. So this is a2 minus a1, and this is given, so it is not 0. So this is 0. So they are saying that there is exist a c such that this f dash c is 0. Okay. Cool. Now let's solve that question. I think what they're saying, there exists a differentiable function fx such that if f dash x is less than 1 and f0 equal to 0 and f2 is 2, there exists a differential function. I mean, oh, sorry, this is true or false. Okay, sorry, I forgot to write. This is true false question. So let's try to solve it. This is false. Vishnath is saying this is false. How you are doing it? So f dash c you are calculating by f2 minus f1 upon 2 minus 1. So this is 2 minus 0 upon 1. This is 2. So f dash c is 2. What they are saying, there exists a differential function such that f dash x is less than 1 for all x. Okay, this is for all x. So it is not possible because there is a c such that f dash c is 2. Something is wrong. 2 minus 0 is 2, right? 2 upon 1. Okay, divide by 2 minus. Okay. So this is 1. Okay. And then they are saying less than 1 for all x, which is not possible because there is a c such that this f dash c is equal to 1. Right? Good. So basically, actually applying this mean value theorem, the first mean value theorem is not very, very intuitive, but I hope you got some idea. Okay. Now let's just solve this gate question, which is very recent question. And I think there is only just one question they have asked from this first mean value theorem. So what they're saying, suppose f is a continuous random, sorry, not random variable. F is a continuous function on this interval and a is a differentiable function in this interval such that every x in the interval f dash x is less than or equal to 2. So basically, let's just apply this f dash x equal to, in this interval, let's just apply this f dash this is f of 3 minus f of minus 3 upon 3 plus 3, right? So f of 3 is what? It is not given. Minus f of minus 3 is 7 upon 6. Yeah, they're asking what could be the at most value of f of 3. Can you find out the maximum value of f of 3? So f dash x in this interval is always less than or equal to 2. So this is given that this is always less than or equal to 2, right? So maybe I can just write here, just a second. So this is less than or equal to 2. It is given to me that f dash x in this particular interval is always less than or equal to 2. So f3 is less than or equal to 12 plus 7, which is f3 is less than or equal to 19. Which means the maximum value it can take is 19, at most 19. A good question, right? Okay. So I hope now you know that how to apply this particular theorem. Actually, only one question they have asked from this particular theorem. Cool. Okay, you can apply any other method if at all you can have. Now, there are some other questions that we have. If you want, you can solve this question as an homework. So these are really good questions. I mean, the solutions are on the next page, but these are really good and intuitive questions also. So these questions are not related to, first of all, the mean value theorems and all. These questions are very nice questions. Like, I mean, I can say, like, I have solved these questions, this type of question in the earlier videos also. So if you want, you can try them out. Okay. So let me maybe just give you some hint and do this midway, and then you can continue later. If two numbers are adding up to 6, so maybe n1 plus n2 are 6, and then they're asking that can you just maximize this n1 into n2, the product. Okay, so what you can do, you can just replace one of the value, which is 6 minus n1, one of the value, and they are asking what is the maximum value of this, right? See, it was kind of constraint optimization, which means within this constraint, you want to find the maximum value. Okay, but you have converted that to one variable optimization, right? I mean, now you have actually included both of these equations. You have finally formed just one equation. Okay, this is called unconstrained optimization. Anyway, so basically, now you want to just optimize this. Now, what is the value of n1? I think you can differentiate differentiate and get the value of n1. N1 will be 3, and since n1 is 3, then n2 will also be 3, right? Then from here, n2 will also be 3. Okay, you can do this, right? Similarly, this is the almost same question that we have. Now, let me just ask you one thing. Okay, currently your graph theory is not covered, but still, let me just ask you one thing. Suppose there is a complete bipartite graph. Okay, graph theory is not covered. You will see that in the graph theory, but still, I'm just asking you. Suppose there are n vertices to distribute. Okay, n vertices to distribute here and here. You may put n1 vertices here. You may put n2 vertices here, right? And total n1 plus n2 is n. And this is a complete bipartite graph in the sense that there is maximum number of edges in between them, right? Do anyone know what is bipartite graph? Actually, don't need to know. You will get to know in the graph theory. But still, I'm just telling you that suppose this is a complete bipartite graph, and then if I just say that you want to maximize the number of edges, yeah, you want to maximize the number of edges will be. Can you tell me? The number of edges will be n1 into n2. If you want to maximize this, then what should be the value of n1? Okay, you can do using the similar method. You can basically put n1 equal to n minus n2 or something, or n2 equal to n minus n1. So you want to maximize n1 into n minus n1, right? If you maximize this, you will be getting n1 as n by 2, right? Okay, so you will see this later, don't worry. Have you seen, do you remember from, if anyone has prepared last year also, do you remember in case of complete bipartite graph, to have the maximum number of edges, we put half and half? We put the vertices half and half such that it is the maximum number of edges. And this is the proof of this, right? You can easily prove this using the calculus. And there are many other applications of this. Of this particular observation. So basically, this is just a similar pattern. This n1 plus n2 equal to n, and you want to maximize n1 into n2, right? The similar pattern we have seen. The similar pattern here, n1 plus n2 is fixed, and n1 into n2 you want to maximize. Similarly, the similar pattern here in this question you can try as an homework. Similarly, like there are, I think, other application is also possible, which is basically, let's suppose that the perimeter of a rectangle is constant, which means, let's suppose the parameter is, I think, 2a plus b, right? This is the parameter. Let's suppose this is some number c, okay, or maybe n, or maybe let's suppose some number 100. Okay, suppose this is some constant number basically, and then they ask you that that if you want to maximize the area, then it means the area must be a into b. Then what should be the value of a and b? Can you tell me? A plus c. From here you can say a plus b is 50. So if you look at this pattern, then it is 25, right? So basically it must be square, which means if the parameter is fixed and if you want to have the maximum area which is possible, then you must be taking the square. Okay, given that the parameter is fixed. Is this understood? Okay, So basically, like I think there are other observations also. So basically, this is the pattern that I have observed over the time. Okay. So basically, this A1 plus A2 is constant, and they ask you N1 into N2. This is some pattern that I have observed over the time. So I just told you these are my observations only. I told you these a few observations. This complete bipartite graph also I like was my observation. And what happened, like before today's class, I was just remembering that okay, in graph theory there is something, there is something. Then finally I got to remember before the class that okay, there was a bipartite graph. So I was just remembering that there is something in the graph theory, and it's been very I think very much long time since I've touched the graph theory, maybe 4 or 5 years. No, I studied graph theory in ISC, but but okay, that also I don't remember now. Cool. So that is all about this derivative, differentiation, mean value theorems and all. So I hope you are now a bit more comfortable compared to the earlier videos that you have seen. Now we are just left with the integration. So we will see the integration in next class. Okay, you can just try out all the questions that are there in the previous year questions. Okay, cool. So thank you so much. And if you have any doubt, you can ask me later. Yeah, thank you, Abhay. Thank you so much. Take care. Bye bye.